Okay, well, Professor Nasser, he's going to talk, he's from Groningen, Netherlands. He's going to talk about exploring the extremes of this nuclear structure in astrophysics and reaction at FAIR, which is a very nice facility. And so please.
Thank you. Do you hear me back there? Do you hear me back there? I speak loudly generally. Well, otherwise I use it also. That's also fine. But then I have to lower my volume. So thank you. Thank you also for the invitation to come to Mexico. I have been to Mexico before. Some 30 years ago, I was in San Diego, and my friends told me, let's go to Mexico. And you can all guess, of course, where we went to. We went to Tijuana. And I said, oh my God, this is Mexico? When I told my Mexican friends, everybody told me, we are insulted, actually. You should not even call that Mexico. You should call to Mexico City. It took about 30 years now. Finally, I made it to Mexico City. So, Roelof, thank you very much for your invitation. I am giving this talk, actually, we have been building up this collaboration for the past, I don't know, too long, I should say, 30-some years, where we are discussing, of course, how to look at the different aspects of nucleus from a point of view of basically reactions, from the point of view of structure, from the point of view of basically relevance to nuclear astrophysics and all these things. So it's a long history, of course. I was the spokesperson on some years ago, but I'm doing this talk actually on behalf of the new spokesperson, who's Joel Podoliak, who probably should also be invited maybe to come and discuss this. He's just actually took over the role of the spokespersonship just a few months ago. So the title of the talk, of course, is a very broad, Exploring the Extremes with NUSTAR. And in order to really set the stage, maybe I just put the 11 most important questions which were raised for physics. And I don't want to go through all these questions, of course. In fact, the neutrino was just discussed before the breaks. So you see, these are really important questions, of course, which are being discussed and investigated by different colleagues from different places. Question number 3 is the one that I want to draw your attention to. And that is basically, how were the heavy elements from iron to uranium made? So this seems to be one of the fundamental questions which is not answered there, then we should probably try to look at it. Again, to continue this sort of setting the stage, I put here the sort of periodic table, of course, the nuclear charts in this case. So where the proton numbers are shown here versus the neutron numbers. And you go down from here, which is basically hydrogen, all the way to here, basically the uranium that you can see. The stable isotopes, which are around 300 of them, are dotted here by black. And then you have this area, which is the sort of yellowish. And this is all the isotopes that we know. This picture is a few years old, so I'm sure the picture has changed, but you would not notice on this resolution anyways. And then you have this sort of greenish, olive green area, which is then the to be investigated area of the nuclear chart. Now, this picture has a lot of information. If you go, for instance, to this side of the picture, so what we actually call, say, the sort of northwest. Then you have the proton-rich part of the nuclear chart. And then you can see that we reach the sort of drip line, proton drip line very fast as you go to this side because of the Coulomb effects that you all are familiar with. On the other side of it, though, if you go to the right, you will see that you can add neutrons and more of these neutrons to the system and still have a sort of stable system, stable isotope. At some point, of course, there also you get to this place where it's called the neutron drip line, and then you cannot have a bound system anymore. Now here, of course, comes the problem. The theoretical models which have some predictive power, of course, they try to say where the neutron drip line is, and they go to this side, to the east side of the picture, basically. And you see the differences are huge. You can have models which have the prediction by 10, 15 units wrong, basically, on that level. So these are very, very, very problematic regions that we are talking about. Of course, when you're talking about the light systems, many things have been done, many things are also known. But our goal, don't forget, our goal is actually how were the elements made beyond iron, of course, but in order to understand that region of the nuclear chart, you better understand this region of the nuclear chart, which is then dealing with light systems. You also see other things here. For instance, this is the neutron halo, where you have two neutrons outside the system in a very light system. It's already lithium-11, where you have that problem facing you. And then you see this, these things are also not quite well explained yet by the theories. So there are phenomena, even at the light systems, which you are not quite understanding. Then, of course, as you go to the heavier systems, you can imagine as you put more and more neutrons into the system, you start to form this sort of skin of the neutron, which is called the neutron skin, for lack of better name. So this skin is basically being formed around the nucleus, around the core, and this core, of course, is made out of the, say, equal number of protons and neutrons, if you wish. And this neutron skin, of course, if you can understand the skin part of the system, this is also good because then you can also go to the neutron stars. And there we come, of course, with the sort of questions which we have also equation of state for pure neutron matter, if you wish. So this has a lot of things. I will also go up here. This is the super heavy elements. And you know that there are a lot of efforts actually going on in this region to see what is the island of stability. Can we have actually heavy systems also up there? What are they and what are their properties, physical and chemical? I will not spend much time here because the talk after my talk is spending a lot of time on that issue. So I will concentrate more on the other items. So if we go further now, the relevance to astrophysics, I put the same nuclear chart now, but now I put all these processes that most of you are familiar with. Of course, the P process, the S process, RP process, R process, all these processes that you have, and then trying to explain basically the stellar burning processes. Now, this is basically, now I just put it here just for your information. The R process is something that I like to pay attention to because that's on the neutron-rich side of the picture. And that's exactly where we also are lacking a lot of knowledge. So a lot of our activities are basically taking place, as you can imagine, for instance, here, right? These are the waiting point nuclei that you know. So N equals 126 is one of the famous ones. This is the third waiting point in the R process. We like to study these things. So I just put it here and you can just pick your process and say, what is the interesting region? And let's try to look at it. Then, of course, we shouldn't forget the theories. Otherwise, Bira will be upset with me in the back. So the theoretical efforts, of course, are very important in order to understand what we observe, right? I mean, you can have any process that you think about. At the end of the day, we are talking about a many-body system. You know, if you talk about lead, for instance, 208 elements sitting there or particles sitting there interacting with each other. Why do they do it like that? Why are they bound like that? So all these things have to be understood based on, hopefully, first principles. So which means that we start basically looking at the nuclei down here. These are the few-body systems. And the understanding these are ab initio few-body calculations are very, very well done. Up until now, of course, there are small problems here and there, but at least the mechanisms behind the interactions are more or less well understood. The reason it's plotted like this is that the width of this picture, actually, the width shows the precision of the theoretical calculations. So at the bottom, you see here this red, which is ab initio calculations, highly precise, therefore a large width. Now we go to higher systems, of course, where you go to A equals, say, 10, 12, and beyond that, then you start looking at no-core shell model calculations, which was also being discussed by one of the speakers yesterday. Then we go to this sort of 0 h bar omega shell model, so the precision gets less, the predictive power also becomes less and less. And of course, when you go up this way, these are the density functional theories, self-conscious and mean field, and all these calculations. Again, hopefully one can use the first principles to get the interactions at least under control, and then the rest is just the calculational methods that people have to come up with in order to get up there. So there was also a talk yesterday in one of the parallel sessions about the properties of very heavy systems based on these new calculations. I'm not a theorist and I don't have the time anyways to go through, even if I had the time, I didn't have the knowledge to really go through the details of these calculations for you. So in order to go and study all these aspects, all these regions, all these processes that I have been explaining to you, of course, we need a huge collaboration, and this is called, in this case, NUSTAR collaboration. I just put it here in numbers for you. This is a collaboration, so NUSTAR is a collaboration of collaborations. There's just what we call the one science, of course, different observables, different instrumentation. So we are basically gathered together trying to address this one question that we have, of course, in mind: how are the elements formed at the end? Now, these collaborations are named here. So these are the names of the collaboration. These numbers are basically the number of people active. There is an overlap between all these collaborations because at the end of the day, our instrumentations are very similar, our methods are very similar, and also the science questions are sometimes very similar, or most of the time very similar. So we have about 1,000 people interested, of course, in the science that we do, 630 officially registered members and 420 senior members. When I say senior members, I really mean people who have a permanent position and are putting their PhDs and postdocs to work on these subjects. Okay, there are 150 institutions from 36 countries on this. Here, basically, you see the same names now in the second column. These are basically sub-collaborations which are formed, but they all have a sort of official status here. However, they have to sort of define their main science sort of subject, science goal somehow in order to sort of justify their funding and all these things. So you can see here, again, you don't have to go through all these names and the topics, but you can see here, for instance, that the high-spec D-spec is one of them, is involved in the gamma spectroscopy at low and intermediate energies, neutron decay, high resolution gamma, beta, alpha, proton spectroscopy. That's basically, so the community, that community comes together basically putting their expertise together on these topics. Another one, R3B, I'm putting here, this is the kinematically complete reactions. I will go through some of the physics and also their instruments just so that you can see what they're doing. But they sort of, as I said, although the final goal is the same, the way we reach there are not always the same, and therefore we need different sub-collaborations in order to get there. These sub-collaborations, as you saw, they are coming in, and this is now the map of the facility. This part, which is done in blue, it is already existing. So that's the GSI laboratory in Darmstadt, as it exists now with all the buildings. And this part, which is done in red, is being built, or is almost finished. The construction is almost finished for the phase 1, which means a lot of these things are almost there. I will show you some pictures. And this is where the collaborations basically are sitting and doing their experiments. They're sitting at different experimental areas because they require the different sort of specifications for the beam and the intensities and all these things. Therefore, they use different parts of the facility. I don't want to go through this extra details now at this moment. The physics program, of course, as I said, the main question is how are the elements made, but that's just one question which basically entails a lot of details. Here is a bit more details about the physics questions that we are trying to address. So equation of state, limits of the existence of matter, lifetimes, masses, probability of emission of neutrons, for instance, fission processes, reactions in star environments. These are the questions that we are trying to address through the different collaborations, or sometimes also common work by different collaborations together. So to address these questions again, we just made this sort of matrix. As I said, this is an overview talk, so I'm not going through all the details of every single collaboration here. But here it actually tells you what you are interested in. Again, I don't expect you to read all these details, but what you can do is the following. Just look at this here. I don't know if you can see that this sort of, like, the resolution is rather low, but anyways, if you're interested in half-lives, masses, matter radii, charge radii, single particle spectrum, collective behavior, equation of state, exotic systems, you just name it. And then with this table, you can actually see these collaborations that I was just talking about. These are the names of all these sub-collaborations that are sitting there. And they tell you basically what they are doing on that front. So just to guide you through one of these things. So if I say, for instance, if I look at the half-lives, this sub-collaboration super FRS is looking at the range from picosecond to nanosecond. So they can go to very, very small lifetimes, basically, and look at these processes, their lifetime, half-lives or lifetimes. Now, this high-spec D-spec, for instance, it can also look at the dressed ions. So the lifetime, they can look at microsecond to second. You see, the range is quite different. Here, for instance, they can, the R3B can also look at the resonance width and decays up to 100 nanoseconds. So you see, every one of them is trying to look at the same observable, but then addressing different parts of the different ranges, basically. Okay? So here, for instance, the super heavy, I think Michel will allude to that further. So they look at microseconds all the way to days. So you can look at also this sort of lifetime. So as I said, this is a bit of complicated picture. Just you can look at your item if you want, and then pick up who is doing what within this collaboration. We want to basically put our focus on 3 big items in the coming years. Okay, because you cannot actually go to funding agencies or even general public and say, look, we are doing all these details. The matrix is too complicated. Nobody will understand. So here is basically what we are trying to say, that we, in the first few years of what we call the phase 1 program, after the machinery is running, we basically like to understand the third process, the R process peak that I was telling you about, around n equals 126. So we like to basically look at that. Look at all the nuclei which are sitting there. We will have comprehensive measurements done by different sub-collaborations, right? Of masses, lifetimes, neutron branchings, dipole strengths, and level structure along the n equals 126 isotone. And this is exactly what I was trying to say. The strength of the collaboration is basically that we can address all these things basically through the different setups that we have. Okay, and eventually, of course, bring the picture together. The second one, the second, say, sort of flagship set of experiments would be addressing equation of state of asymmetric matter by means of measuring dipole polarizability. Remember, when you do asymmetric, you have this sort of neutron skin that already puts you the asymmetric case, and there already, by definition, you can excite the dipole modes very nicely. So we can look at the, dipole polarizability and also the neutron skin thicknesses. These are, of course, focusing on the isotones of n around 82 or larger. And the third topic would be the study of exotics. So in principle, nuclear physics, we have neutrons and protons, but you know as well as we do, of course, that you can excite also hyperons into the nuclear system. So we can study also the exotic hyper systems, right? Again, this you can do with large NZ asymmetry. Of course, traditionally and also in the past, many people have done nuclear structure studies also with the hyperons, right? But this is basically very light system, very symmetric. The goal here is basically to go to large NZ asymmetry. For this, of course, we need many, many parts. And by parts, I really mean experimental equipment. So here is basically the parts in brief. So here we have this super FRS. This is the fragment separator. I'm not plotting the accelerator, which is behind it. So the beam is delivered here at this target position. And this is a sort of spectrometer of about 200 meters long. It's a very long spectrometer. And by making it this long and also having all these bends here and these dipoles basically, and also the secondary base, what we call the degraders, you can actually separate all the ions that are produced and just pick the ion that you want. This is shown in the top picture here. So you can here see this. This is a sort of enhanced picture of this. Pre-separator, the main separator. So you can, after this collision here, you get a sort of cocktail of a lot of particles. Most of them you don't even want. If you look here, in this particular case, I'm interested in this particle, but look at all these guys which I don't want. So in order to purify that, you go through the stage. So this is the first stage. You go through this one and you reduce the numbers by this much. You can just compare the two. And then you go through another stage, and then this is what you get at the end. So this machinery basically is capable of producing the ions that you want with a very high sensitivity. And when I say very high sensitivity, I'm talking about 10 to the power 15, 16, 17 sensitivity, right? That you can single out the ions that you want or the ions that you want from the undesired ones at that level. Not only that, we can eventually take one ion out and use that one ion and study it. Okay, so it has two aspects. Sensitivity and selectivity are there at the same time. All these experiments, again, that I was telling you about, so after all these things that happen, then the beam is sent to the experimental area, whether you're doing mass measurements, for instance, laser spectroscopy, and all these things, which also will be discussed in the next talk. High spec, D-spec, this is just the gamma spectroscopy. Then you send the beam to this area. If you want to have higher energy reactions, for instance, you send it to this area. And if you want to do ring measurements, you send it to this area. Unfortunately, because of the budget limitations that we have had in the past few years, this part of the facility will be not done or will not be done in the upcoming period. So it's postponed officially. Now, one of the big advantages, the way we can do this, and the big advantage that we have over other facilities, of course, we have ESRIG, we have the Japanese facility, which is running at in Tokyo, of course. All these things, they exist, and they have existed in the past. The major difference between these facilities and the one that we have is just the energy. So if you look at all these facilities, you can see Ganil, you know, the NSL, the ESRIG, RIKEN, of course, is sitting here. These are basically the energies that you have, and they go up to about 200, 300, 400 MeV per particle. The advantage that we have, and it's actually a big advantage at some point, is the higher energy that we can reach up to 2 GeV per particle. And the reason for this advantage is that if you look at this line here, this line is basically where the separation comes from 90% of fully stripped ions. So you take an ion, you fully strip it, right? And then you need the energy in order to fully strip it, otherwise it will not work, right? It will recombine again. So the higher the energy, now you can see this plot goes as the element number. The higher the energy, the higher element number we can actually have in the pure form. That's basically the advantage. Now, if you have that advantage, then you can go to very heavy systems, of course, and do all these measurements. With these higher energies, if you look here, for instance, you can see the Coulomb excitations up to 13 MeV is possible only at this energy. So these other laboratories cannot get up to this energy, right? It's just kinematics. We can do delta excitation. These were the exotics that I was discussing. You can have hyperon production at this energy, right? Which you cannot then do at the lower energies. So this is sort of the major advantage that we have over the other facilities. The other thing that, of course, has now happened is that we had a small fragment separator. It was called FRS, and I just called the other one Super FRS. That's a big fragment separator that we have. And this separation just happens at this level. Sorry, I'm going the wrong way. Right? This is basically the separation that happens, right? So the present one is actually something like 20, 30 meters or 40 meters, I think, and it will go up to 200 meters in the future. So with that, of course, the magnets are bigger, the acceptance of these magnets are better, and we improve our transmission. So there, of course, depending on the type of ion that you're looking at, for instance, here, if you look at the Z of 20, the gain factor will be around, say, a factor of 10. So you already win a factor of 10 with the new facility. We win another factor of 100 because of the production accelerator, which is before all these things, right? And putting it all together with all these improvements that have been made, right? The total gain factor compared to, say, 10, 15, 20 years ago will be about 10,000. So we can actually, somebody was talking about the intensities, of course, before the break. So improvement factor of about 10,000 will be achieved compared to 20, 25 years ago. Most of it is actually realized up until now because the injector, for instance, has been now already there. So it's working. So we are going in that direction. So we are improving as we go. All right. So the strategy, of course, we basically, since this took a long time, the first discussions on this facility started already in the late 90s. So you can now imagine the first beams coming out of this big site synchrotron will be in 2027. You're talking about 30-year work. In this 30 years, of course, people are not sitting still. So we define our strategy in different phases. We called it phase 0, where we are doing the R&D of the experiments, we are building the devices, but in order to use them, to understand them, we took the device to a different facility, for instance. We call that phase 0. So we went to Japan, we went to ESRIG, for instance, and all these places, and we did experiments with the devices. The phase 1, of course, is the phase where the beam is produced by our own machine at GSI and FAIR, and then we use that beam and then couple it to the devices that we have developed in the past 2 decades. And then, of course, we go to phase 2, where the full machine is there, and then phase 3, which is the new elements and all these things. And this goes way beyond my retirement, so I'm not even worried about it. As I said, I mean, I was very young when we started with this, and I'm close to my retirement age. So then we go on with this. So the emphasis actually on this phase 1, which is starting in hopefully 2027. So this is basically the approach that we had. This is the old machinery. So here is a synchrotron. This is called SIS-18. So this is sort of smaller synchrotron compared to the future one. We had the ring here. We had this FRS, which I was telling you about, this small fragment separator. And we had the experimental areas here. And these were different sort of places where we do experiments. And of course, this sort of slowly evolves into this facility, right? So this old facility was this one, and this new facility is this one, okay? So it's way bigger than the old facility, more powerful and all these things. And it is, that was of course in the picture. In reality, this is being built as we are talking. This picture was done in September 2021. And you can already see this building, which is bringing the super FRS. And then you have this higher energy experimental area, the lower energy and all these things. So there's a lot of construction work going on. This is basically where I was talking about. This is the low energy and the high energy buildings for the different experimental collaborations. And then, of course, this was 2 years ago, 3 years ago, actually. So this is what we have now. This picture was taken. This picture was taken just a month ago, 2 months ago. So you can see the ring is already completed. Actually, the buildings are on top of it. So everything is finished. And then you can already see this was the high energy building, the low energy building, the super forest building, and so on and so forth. So it is, as far as the civil construction is concerned, the first phase of the construction is finished. They're putting the magnets already in there and sort of connecting them for the commissioning in 26, 27. So I put this back again, and I will now go through some of the science. I don't know how much time I have. I have to adjust myself also. Okay. So then look at this list again. So these are the different sort of sub-collaborations as we discussed. So let me just go through some of them, give you just a flavor of what they are doing in the coming years and what they have been doing in the past. R3B. So R3B, this is the plan for future. I told you because of these higher energies, we have access to high excitation energies. For instance, Coulomb excitations, we can go to higher excitation energies. And this is one example of what I had in mind. So here, for instance, if I look at the cross-section as a function of the, say, photon energy, this is just a classical picture. You can just do the excitation by photons or electrons. The maximum that people have been reaching is about 7-8 MeV in excitation of this sort of thing. This is on helium-4. And if you look at now what we intend to do in the future, this is, again, the same photon energy equivalent. So one can go up to 40 MeV excitation. And then you can see that one actually probes completely different structures of the same nucleus. Actually, this is helium-6, but the same part of the nucleus is the same, roughly. Okay, so this gives you a sort of what I was talking about. If you talk about the polarizability of the nucleus, you need to do these measurements. Okay, and you have to go to higher energies. And this actually shows you, again, the resolution is probably not good enough to see all the details, but this also has to do with the fact that if you wanted to look at the dipole polarizability, I don't know if you can see this from the back, you have to integrate this cross-section basically all the way to infinity, right? And then if you don't have the excitation energies, if it stops very soon, of course, then you cannot integrate to infinity. So you need these excitations in order to measure this integral. Sorry? I don't. Oh, these cross sections are just basically the sort of equivalent to Coulomb excitation, basically. This is differential cross section as a function of the sort of excitation energy, which is then the opposite is the same. Also, this is also I think this experiment is even from electron scattering. So it's just the electron scattering cross section. Excitation energy is omega, right? That's how you excite it, the final energy minus initial energy of the electron, and then you just measure the cross section. But this one is done with I think this case is done with a lead nucleus as a sort of instigator of the Coulomb excitation, okay? So in the field of the nuclear field of this lead. So you can do this sort of cross sections and then integrate to infinity. This is actually done. This is an experiment done. And the calculations actually is done by Jorge, who is also in the audience. So he can explain to you all the details if you want. And then in the future, of course, the idea is basically to go to lead chain. This was actually done in the nickel. So you can go to very heavy systems and go all the way up to 25 also, and really measure this dipole polarizability as I was discussing. That's one example. Of course, that's simple measurements. Of course, you need a huge machinery. So here I have this glad magnet. This is a superconducting magnet. It's actually the size of it. If I put it here, it will take this stage completely. You know, it's a huge magnet, just to put you on scale. And you can now imagine that you have all kinds of the detectors. So this is the neutron detector. These are the proton detectors. Khalifa just goes around the target area and just measures the photons and protons which are coming from the target, right at the target position. So you need a lot of detections, and the countries which are involved in the collaborations are basically listed here. So here is now another example of what was just done recently, just to give you a flavor of this type of experiments. So here is basically the measurement done carbon-12 on carbon-12. This is a benchmark case, and as a function of energy. So this is the beam energy, MeV per nucleon, and then you have this interaction cross-section. This interaction cross-section, of course, you can just do from the reaction and then subtract the inelastic and all these things. But the precision which was obtained here is this precision, about 0.4%. Very high precision measurements done. And these are basically the data that are shown here. This is compared to, say, the old data, which are much worse. And this is compared now to Glauber calculations. And you can see this scale, by the way, is not from zero. So don't be misled by this sort of magnified here. But you can see that the Glauber calculation, albeit so reliable, still is 2.5% above, say, our measurements. So you need these precise measurements in order to proceed with this. Another example is the neutron skin. People who are familiar with the P-Rex experiment at the JLab, you see this is done on lead-208. This density is plotted here. This is called the weak, I think the weak density they call it. And then here, of course, the charge, which was obtained long time ago, actually 3-4 decades ago, I think. And then at some point, you can also do the matter radius. So you can have the matter radius and then subtract the charge, and then you have the neutron skin, as it were. Now, P-Rex, of course, measured it more or less directly. So there are these methods which are being done, and the studies are done. This is a fission experiment. The fission experiment is done, and you can see this is in the area, this heavy area. Of course, you can see the names of the nuclei here. And all these things which are plotted here means that this fission has been measured for that nucleus. Okay, many measurements done in just one shot, because we have a huge acceptance, we have a good data acquisition, basically, which takes all these things at the same time. So very efficient. This is all the new sort of detector systems that we have developed in the past 20 years or so. This is another experiment where short-range correlations are measured. This is you look at the high momentum fraction, basically, of the protons or the neutrons which are coming from a certain nucleus. In this case, you see the nucleus is carbon-12. You have tin 110, tin 120, tin 132. And you even have carbon-16 here. So these are the measurements which are done also at JLab, by the way. The same measurements have been done with electron scattering, right? So you just shoot out basically the proton, and you do PN, for instance, PN measurement, and then you look at the correlations inside the nucleus. And you can see that this is for asymmetric systems. You have the neutrons and the protons, of course. As you go to more and more asymmetry, you see that the amount of this ratio, the ratio basically changes, which means that the correlation is also changing depending on this N over Z ratio. And these devices have now been put in place in the old building, actually, trying to also do these measurements that I just alluded to. So it's the same sort of device. This is the same magnet that I told you is about this big, the stage big here. And experiments have been running since 2017 with this setup. Again, this setup is still not complete, so we are building as we go. And finally, the complete system will be placed in the new building, which is going to be ready soon. So this is high spec, D spec. These are the gamma spectroscopy. I said the goal, of course, at the end of the day, will be to sit in this third waiting point. This is the R process around N equals 126. And I put here these circles here just to indicate to you what I mean with these different phases. So this small circle here is phase 0. This is what we can do today. We cannot even go beyond basically these isotopes. That's because we don't have the intensity. Very simple, right? You can only go to these very neutron-rich systems down here when you have these high intensities coming up. So this is basically the phase 1 and phase 2 and so on and so forth. So you can see how the progression is done, and eventually we should be able to cover basically the third waiting point completely. So these are all the nuclei which we are aiming to measure. One example is actually recent measurements which have been done on the lifetimes. And if you look here, for instance, these are the sort of extracted lifetimes already, the dots here, the circles. The predictions with the old lifetime measurements are basically shown here in the red-black line. These are the predictions which do not agree anyways with the observation, so there was already a problem. The new lifetimes which have been measured actually made the disagreement even worse. But these are the new lifetimes which have been measured. Oh, now I have to move. So here is basically where they put all these detectors, right? So the Fatima, these are the photon detectors. Many of you are familiar with the Agatha, of course, which will be at some point also put there for measurements. So they have these small detectors which are also measuring the implantation products and all these things. So I need to move a bit faster. By the way, as I told you, these detectors which are developed in phase 0, they were actually placed at RIKEN to do measurements there, and results have been published. Maybe I then move a bit faster here because I'm only having 5 minutes. So here is basically the isotopic chain. This is the lifetime measurements, because as I said, there is a problem in this lifetime measurements. So people want to do now more and more of these measurements basically in this region. So the setup is being completed soon for these measurements. Some measurements have been done already this year, and some will be done also next year. So here also they put the limits, for instance, of 10 minus 10 millibar limit, 10 minus 9 millibar limit. So you can see, based on the limit and your luminosity, which nucleus you can actually measure. Then I go to MATS and LASNPA. These are the mass measurements and laser-based spectroscopy. Due to the problems that we have had, basically we don't have this sort of facility for them yet, so they developed all these things and they took them to different laboratories. They have done measurements basically in Uvascular laboratory. They have also gone to the United States, Argonne National Laboratory, to do some measurements. And here basically the numbers are there. These are very small now, of course. These are basically, the N is about 72 here, Z is 40. So that's the region where MATS and LASNPA are sort of concentrating to measure basically the masses and also the lifetime. So here is basically the mass measurements of zirconium 110, for instance, palladium 126, and osmium 200 are being aimed for. These people are also involved in the developments of the CRIS, which was also discussed before the break by our colleague. So you can see that there is a lot of course, collaboration, also cross-collaboration with other collaborations around the world, right? So here is this penning trap and coupled basically to the system. And the example was also shown yesterday in one of the parallel sessions. These are not very large devices, of course, very small, but very, very high precision and also difficult to make.
So with that, of course, I'm coupling it to techniques, which I think Michael will also allude to, right? So you will discuss these techniques, so I will, due to lack of time, I'll just skip this one and give the word to him. So laser spectroscopy, again, which he will discuss, is being used to look at these resonances and also do the measurements, for instance, for the different observables. ILIMA is another example. So he will, you will hear more about these techniques from Michael, the next talk. So ILIMA, of course, is the ring measurements. So in this is the present facility. So the fragment separator sends the beams into this ring. And then here, for instance, you have a time of flight detector. And the way they do this sort of things with the isochronous modes and all these things that you have, you can actually separate, because you make the revolution, say, 1 million times a second, you can separate the different masses very nicely with these detection techniques. And then with a high resolution, actually, that you can do this. I will show you one example. All these masses, by the way, they have been measured here, for instance, with this technique. And now with this, of course, you can now see what is the difference between the mass and liquid drop. Model differences are shown here for cadmium, tellurium, and tin. Here is an example which I really find very nice. This is the detection of an de-excitation of, say, germanium-72 from the 0+ to 0+. And the quantum numbers, of course, force you that you cannot do just a single photon decay. So you need to have 2 photons in order to go through this decay. And these 2 photons, I mean, the masses are, of course, the lifetime is known, the energy, excitation energy is known. The power of this technique is shown, oh my God. The power of this technique is shown actually in this picture, where the particles are coming from below. This is the time going up. The particles are going from below and then decay inside the ring as they are revolving. So once they decay, of course, their masses changes by this excitation energy, right? So you can see that they disappear here. This is the excited state. They disappear here and they go right into the main one, right? So the mass changes and they shift to a different orbit. And this is the precision, how you can actually measure the excitation energy. Very high precision. But my time is really up. And can I have 2 more minutes, 2 or 3 minutes, just to discuss one effect, and then I will just this exotics that I was telling you about. There has been a puzzle, of course, in the past years about the lifetime of the hypernuclear, hypertriton here and hypertriton 3 and 4. And this puzzle, of course, it has been there for the past few years. And also there is another question, does NN lambda, for instance, exist or not? These 2 puzzles, of course, were the focus of this experiment, which we call them the sort of exotics, okay? So this has been done now. The data are being analyzed, of course. And in order to see what we are talking about, this is basically the old experiment which was done. And with the new experiment that we are now doing, we have done already, you expect to have this sort of resolution compared to this sort of resolution. Major improvement in the resolution. And hopefully, we can determine the lifetime with a higher precision compared to before. So if you look at this is basically the sort of on the drawing, and this is in reality. And this is the size of this detector, so somebody can even sit in it. And this experiment has been done. Unfortunately, we don't have any results to show at this moment. So with that, I think I will also, we have had major efforts also in new isotopes. I showed you the sort of nuclear chart at the beginning. Now you can see, of course, we need to really, one by one, find these new isotopes and then register them and hopefully measure their masses and their lifetimes and so on and so forth. So I will end here. The super heavies, I will leave to my next, the next speaker. So let me just summarize, so I'm at the end. I tried to show you how much work it is actually to understand this nuclear chart, from the light systems here, where you have this sort of phenomenon, nuclear skins, all the way up to super heavy elements that have to be studied. And for that, of course, we need a huge collaboration, basically addressing all these things that I also showed you before, in order to get different observables, of course, in different ranges of lifetimes, masses, and all these things. Sensitivities have to be studied. And this is basically, with this, of course, I leave you with the picture, and thank you for your attention.
Well, thank you for the nice talk. Now the session is open for questions.
So,
Well, I have a little question about collaborations. You talk about many collaborations, but can you comment on collaborations with Latin American, and for the students, what you have for them?
well, I mean, look, we of course, we welcome any new collaborator from anywhere. And we have been to several places, including Brazil, some years ago with the director of FAIR to sort of make the advertisement for this facility so that people come. We do have people who are involved, but there are some financial constraints from what I understood in Brazil, for instance, that the money cannot be allocated easily to different laboratories, across the globe, for instance. But collaborations are open. So if you're interested in any collaboration, you can certainly join us. Especially, for instance, why we want to advertise this, our own university has a collaboration, official collaboration with this university here, right? Which means that any student who is interested in doing some work, of course, we have joint PhD programs, which are then partly financed by this university, partly by our university. And through us, of course, we can set up these collaborations also. I'm sure GSI has the same program. I mean, it does exist also at GSI, these sort of things. I mean, Michel can also comment on this. So we do have a lot of these the sort of double degree program, you want to call it, or whatever you call it. They do exist, and I encourage especially the younger students, because you form the future of us. Why am I looking this way? Because most of them, I think, are sitting here in this corner. But certainly open for further collaboration.
Okay, thank you. Are there other comments or questions? Okay, so let's thank the speaker.
Well, thank you.
Well, now I would like to call Michael Block from GSI and University of Mainz. He's going to talk by exploring the structure of the heavy nuclei through laser spectroscopy and mass spectrometry.
Yeah. That's okay. Yeah, I just need a little more cable maybe, and then we can do. Yeah, well, thanks a lot for inviting me to this nice conference. It's my second time that I attend one of these nuclear physics symposiums in Latin America, and I very much appreciate the breadth in the program, and yeah, I hope I can contribute a little bit to it. Before I start with my talk, I just finished the comment to the previous question that Gilberto asked. There is, of course, a program which we call Get Involved, which allows students on various career levels to work with us at GSI and FAIR. And we have also an international summer student program since, I think, 25 years, where people from all across the world can come for spending 2 months with us in summer. And usually the deadline is, I think, in the end of the year in November. And then you can certainly take a chance to work with us. Okay, now let me start with my science part. Okay, I have to first still set up a little bit myself here on the stage. Yeah, so I will talk about what we call super heavy elements. And yeah, of course, this is an endeavor which needs a lot of people. So before I forget it at the end, because I'm running out of time, I want to acknowledge many of the people involved. This is my own groups. I mean, I have a dual appointment at the University of Mainz and at the GSI in Darmstadt. So also my group is split up in 2 parts that, of course, work on the same problems. And then there is a number of international collaborations. This is the one involved in the mass measurement program with the so-called ship trap facility. As I will also show you, we have a bunch of laser spectroscopy activities. And one thing I will particularly talk about in some detail is experiments on the element fermium that are also connected to samples that we obtained from the Oak Ridge HIFA reactor that Alfredo introduced to us. So this needed an even different collaboration. Oops, here you see some of the people, for example, Klaus Wendt, Norbert Trautmann, somewhere there should be Christoph Düllmann and Tom Albrecht Schönzart that made all of this happen. Yeah, and here you see a few more people from the different laser spectroscopy groups, where we, for example, have a very strong collaboration with people from KU Leuven, but also many other places worldwide. So now I can start with a menu, what I will try to discuss. I mean, as I understood, this audience is very mixed, so I have decided to spend a significant time of my talk in a relatively broad introduction, telling you the status in the field and the open questions. Eventually, what is the main challenges? I will focus a little bit on experiments, as I said, that we have done in the last 2-3 years on fermium isotopes, and then, of course, come to a conclusion. So let's first look in what are super heavy elements. I mean, I'm an atomic and nuclear physicist, but technically I'm in the chemistry department at my university, and my chemistry colleagues always tell me every talk has to start with a periodic table. So I do not want to break this trend, so I also do this, but to make it a bit more interesting, I have picked one that is quite a bit old. I mean, you should keep in mind the periodic table has been established, I think, around 1865 by Dmitri Mendeleev and Lothar Meyer. And at that time, they didn't sort things by atomic number yet because they didn't know quantum mechanics and many other things, but the periodicity prevails. This is around before World War II. And I mean, it's maybe not much of a surprise that around uranium, which is the heaviest element more or less naturally we can find on Earth. So this was more or less where the periodic table ended at that time. But people were aware it is incomplete, and at least they had already prepared some room for elements up to, let's say, 100 at that time. Now, if you look into the discovery starting around 1940, you see there is a regular discovery, but there are some gaps in between. The gaps usually occur when you have to develop a major new method. Initially, what people would do, they take the material that they have, which was the uranium, made it a target. And at that time, as we had heard in one of the talks yesterday, of course, Berkeley had the cyclotron. Yeah? So they used the cyclotron to accelerate light particles, to make fusion reactions, and then radiochemically separated the new elements. At some point, though, the radiochemical separation was not fast enough and maybe also not sensitive enough, and so physical methods had to come, and then heavy ion fusion evaporation took over, and then eventually many of these elements were discovered in what we call cold fusion, and then later on the so-called hot or warm fusion came up, and this resulted in the discovery of the last elements in our system. And so presently, the heaviest element that we have been able to observe has the atomic number 118. So if you take a table of a periodic table as it looks today, you have this sort of familiar picture. I have highlighted to you in blue the actinides. I mean, this concept was put forward by Glenn Seaborg, and he received the Nobel Prize for it. And here you have what the chemists would call the transactinides. And this is what we in physics usually refer to as super heavy elements. Of course, some of the information here in principle is scientifically speaking premature because nobody has ever studied, for example, the chemistry of element 118, yet we put it into the sign in the table with the noble gases. If you ask state-of-the-art theory people to predict what is the state of organeson at room temperature, they will actually tell you it's a solid. So it's potentially not a noble gas. And the reason for this are so-called relativistic effects. Now, if you look into this, you can see here an example. So here are calculations for different noble gases. This is the organeson, this would be radon, and this would be xenon. NR is the non-relativistic calculation, and R is the relativistic, so solving basically the Dirac equation. And you can, of course, see a couple of things that are typical. I mean, for example, S1/2 or P1/2 states, they would be stabilized, so there is a relativistic contraction that you observe. But for example, D5/2 or P3/2, they would be less bound due to the screening effect. Now, another thing which is remarkable, if you look from an atomic perspective, I mean, we've heard in previous talks about laser spectroscopy and fine structure and hyperfine structure. Normally in light atoms, the fine structure is a small perturbation, but the fine structure in organeson is almost 10 electron volt, which is in a typical energy that a chemical bond has. So you can see these elements really are different. Yeah? Another thing is referring to this contraction aspect. So this is a radial density of different wave functions. Again, you have different calculations for relativistic and non-relativistic. So the dashed line would be non-relativistic. So you can see the radial densities goes closer towards the nucleus. Yeah? You see really a contraction, and that somehow also changes the orbitals that interact in the chemical bonding. So also chemical properties will be changed. And I mean, of course, usually we deal with around 100 electrons in an atom that have to talk to each other. So when we want to make calculations, we have to take into account, well, of course, well, first of all, let's say the interaction, the correlation between the many electrons. But the other thing is, of course, as Z alpha is approaching 1, we cannot make this simple 1 over Z alpha expansion for the QED contributions that at some point also will become sizable. So there are many fundamental aspects also from the atomic part that we can look at. And I mean, this will eventually determine also limits of the periodic table. I mean, one aspect, if you remember solving the Dirac equation, you had to deal with sort of negative energy solutions. And here you see calculations for the energy of the 1s state as a function of nuclear charge. And FNC means a finite nucleus. Yeah, so you have, of course, not a point-light nucleus, but a finite-sized nucleus. And that changes where this starts diving into the negative energy continuum. And this happens around atomic number 172. So eventually you would probably run into a problem by not having a normal atom. But as we know, before this limit will be reached, we expect that we do not even have stable nuclei anymore that would be able to form an atom. So most likely the periodic table will end well before this limit can be reached. Even though some people have already thought about how the elements could be arranged in such a case if these elements were to exist. If you look into the experimental status, how many atomic levels do we actually know? Then you see, well, not so many. I mean, already at the heavy actinide, so californium is element number 98. You see the green data points. These are experimental data which are relatively old from a compilation by Blaise in 92 already available. And then the orange data have been added in recent years. Many of them by our own work, and the blue ones are theoretical calculations. So you see already around atomic number 100, the experimental data set available to us is very scarce. Yeah? And this is because the availability of these elements is highly restricted, and we can only produce them in small amounts, which require very sensitive techniques. But these theoretical predictions are very important to guide the experiments that we carry out. So what is special about the super heavy nuclei? Well, of course, first of all, their existence is due to shell structure. So the quantum mechanical shell structure gives additional binding energies on the order of 10 MeV. And here is an old picture that I borrowed from Sigurd Hoffmann. The calculations had been done by Adam Sobichevsky. And you see here in the blue line is the sort of the one-dimensional binding energy is here shown as a function of deformation. Yeah, so zero deformation would be spherical nuclei. And you see for elements 98 californium, 106 seaborgium, and 114 flerovium. Here you see already the droplet model, the liquid drop model would not give you anymore a barrier against fission. So these heavy nuclei would simply disintegrate by spontaneous fission. I mean, this is the main competition when we try to add more and more protons into the nucleus. However, you see the shell structure gives rise to bound states. And I mean, you can see in this model, The 114 would supposedly have a spherical minimum, whereas the Seaborgium, for example, as we know, is a deformed nuclei. The majority of the super heavy nuclei that we have been able to produce until now are deformed. We have not yet been able to reach the next region where spherical nuclei are expected to occur. And so in principle, from the nuclear physics point of view, we can say all the nuclei that only exist due to additional binding by shell structure compared to the drop model is what we would call super heavy nuclei. And I mean, depending on the parametrization, the cut comes at around, let's say 106, which is close to the 104 where the chemists call transactinide. So we usually stick to the convention that around 104, we call it super heavy. Yeah? So if you look into the landscape of what is nowadays available, you see all the colored squares here show nuclei that have been synthesized. The dark blue background color is the shell correction energy. So the darker the blue color is, the stronger is the gain in binding energy by shell effects. And here you see this region, which has been at some point in the maybe late 1960s coined the island of stability. I mean, I will address this in more detail in one of the next slides, but this is sort of the region where people would like to go, and this is where we would expect again spherical nuclei to occur. However, this is at a neutron number of 184, and this is about 8 neutrons more than the most neutron-rich isotope that we have been able to produce. However, if you think about theoretical predictions, I mean, presently we only know one isotope of element 118, organeson. Theory predicts there should be about 100 isotopes existing. So we have at least 99 more left to be discovered. Now, the island of stability term, yeah. So first papers of this came out in, yeah, I think mid-1960s. I mean, for example, Sobichevsky and Gareev and many others. And then here's around the early 1970s, some calculations were made about the spontaneous fission partial half-life. And here you have for reference some experimental data for elements up to curium, which is element 96. Yeah? Here you have fermium element 100, and here you have some reference data. So as we know in curium, for example, the fission half-life is already considerable and they are very long-lived isotopes. And here in these calculations that I show you here, at that time, there was even a prediction that the fission half-life in this region at neutron number 184 or so could exceed the age of the Earth. And that would have meant that super heavy nuclei could exist on Earth. And I mean, this has triggered a lot of search activities which have not given unambiguous results. So for the moment, we have not found any of these nuclei on Earth. And nowadays, the theoretical models also do not predict these long lifetimes any longer. But I will address this in more detail in one of the next slides. But this is where the name and the somehow story came about. So let's look a little bit more closely. I mean, this is a plot I took from a very recent review article. And yeah, so what you can see here, the gray area, this would be the beta stability region. Yeah? And you see we are still a few neutrons short from there. And yeah, here you see potential predictions for the center of the long-lived region. I mean, different models still come up with different sort of magic numbers, if you want to call it like this. And now, why is this so different? Well, if you first look into experimental data, we can indeed say these are data from alpha decay. Yeah? So if you have alpha decay half-lives as a function of neutron number for several isotopic chain, you see there is a clear increase in the half-life. So the general concept of an island of enhanced stability is indeed valid because the dominant decay mode for many of these nuclei is alpha decay. And this is really clearly shown. And you see we are still, again, not here. So this might really lead to sizable half-lives. However, at some point, the half-lives might be such that the alpha decay is not the dominant decay mode, but beta minus decay, electron capture, or whatsoever may kick in. But the biggest issue still remains nuclear fission. Because if you now ask, nuclear models, which are really sort of state of the art, which can make accurate predictions of known properties to make a prediction. What is the heaviest nucleus that exists in your model and what are the decay properties? This is what you get. So one model predicts element 120, isotope 300 to be the heaviest one that can exist, but the lifetime is only 10 to minus 5 seconds. Here you have a case where Darmstadtium-294 is the longest lived one and the lifetime is 10 to 5. Yeah? So you already see here tremendous differences. Now, of course, to compare further what we have done, we have asked the theoreticians, please calculate a known nucleus where we have experimental data for the half-life. And this was Copernicium-284. Experimentally, we know it predominantly decays by spontaneous fission with a half-life of 120 milliseconds. And these are the theoretical predictions that come out. And you can see here, there's an 11 orders of magnitude span in fission. I mean, you know, fission is a tunnel effect, so you expect some leverage on this, but 11 orders of magnitude is substantial. So apparently there is a big need for a very detailed microscopic discussion of fission in great detail. And of course, we have to also provide experimental data that allows the models to be benchmarked. But this is really one of the crucial stories that is still open. Now let's look into the experimental challenges. What do we have and how can we produce it? Let's come back to the periodic table for a moment and look into this. So in the periodic table, well, of course, we can start from stuff like here, I mean, which we have, I mean, uranium you can get from a mine, you can get tons of it, you can use it for energy production. So this stuff is easy. But already here, when we approach, let's say, Californium isotopes, we are talking about a few milligrams that can be produced. In Einsteinium, you can typically make a few nanograms per year. And in fermium, as I will show you, you make, if you're lucky, you get a few pico or femtograms even. But in fermium, the macroscopic, I mean, what we call macroscopic amounts terminate. And from that on, we have to deal with individual atoms at a time. And this can range from a few atoms per minute down to a few atoms per day. So if you typically run such an experiment, you can produce around one, let's say, an organeson atom maybe per week or per few 3-4 days, depending on your accelerator. Yeah, the half-lives that we have for the longest lived isotopes range here a few minutes, here even on the hours, and here we are somewhere below seconds presently. I should also highlight the beams. I mean, calcium-48 used to be a key beam and is now in a critical situation because since Russia decided to invade Ukraine, the isotope market has changed. The global isotopes of this type usually came from Russia. So many of our programs have no access anymore to calcium-48. So we cannot simply buy it. Situation is different for titanium-50 that is available on the market. So this will also become a more important beam for the future experiments. While also the actinide targets are, of course, of big importance, and they come most of the time out of the Oak Ridge reactor, and then they have to be prepared to make them a target, and this is done by our nuclear chemistry colleagues at the University of Mainz, the group of Christoph Düllmann. Now let's look into the typical production scheme for the online thing is fusion evaporation. You accelerate a projectile, calcium-48 or similar, to an energy close to the Coulomb barrier, so say 5-6 MeV per nucleon. Then we have a target which has a thickness of about 0.5 to 1 milligram per square centimeter. And then we can have a production. Ideally, we fuse. If we are lucky, we build a compound system that survives. And then after some de-excitation by the particle evaporation, we can end up with an evaporation residue. Now, typical beam intensities for the primary beam would be on the order of 10 to 13 particles per second, whereas in the highest case, we only get 1 particle per second out. So that means we need to use electromagnetic recoil separators to get rid of the primary beam in order to have a chance for our studies. Yeah, at the GSI, we are in the lucky situation to have several setups. I mean, we are still using the Unilac accelerator, which is in some variations in existence for almost 50 years. It can be served by several ion sources and provide beams of about, as I said, 6 times 10 to 12 particles per second for relevant beams for super heavy experiments. We have 2 major recoil separator, the gas field separator TASCA and the vacuum velocity filter SHIP, which is in the straight line of the accelerator. So let me start with a few examples of experiments that we have carried out. And the first one is going to be about mass spectrometry. Why do we care about masses? I mean, this was also discussed in a few talks already in this conference. I mean, the binding energy is, of course, an important parameter of describing a nucleus. And as we have heard, several binding energy differences like neutron separation energies or 2 neutron separation energies and empirical shell gaps, they allow us to see, for example, shell structure. I mean, here you see some of the pairing from the odd-even staggering. Here you see, for example, the known neutron shell closure in lead in N126. Yeah? And similarly, we expect weaker shell closures at neutron number 152 and neutron number 162 in super heavy nuclei. So this is information that we can get from nuclear masses. One way to measure nuclear masses is using a so-called Penning trap. A Penning trap is a configuration of electrodes that can look, for example, like this. So if you take these 2 upper end caps and this middle ring and you apply a positive static voltage, you can make an ion oscillate along the axis. And if you superimpose a homogeneous and strong magnetic field, you get the trajectory that is depicted here in black. This can be decomposed into 3 eigenmotions, but I don't want to bother you too much with the detail. I mean, the important message is that the radial motion is connected to the cyclotron frequency, and the cyclotron frequency depends on the charge, the mass, and the magnetic field. I mean, since usually we want to measure this on a high precision meaning 1 part into 10 to 9, then we normally have to also calibrate the magnetic field. So normally we do frequency ratios where we measure the frequency of a known ion compared to an unknown. And if they have the same charge state and measured at the same time, then the magnetic field and the charge state cancel out. And then the frequency ratio is sort of proportional or inversely proportional to the mass ratio. Now, how can this be done in practice? I mean, we have actually pioneered mass measurements in the region of, let's say, mass number 250 back in 2008, and we have used the so-called SHIP trap. This is a solenoid 7 Tesla magnet, which houses 2 Penning traps. I mean, first, of course, you have to slow down the beam. I mean, the recoils come out of the target with about 40 MeV energy. We slow them down in ultra-high purity helium gas at 40 Kelvin. The slowed particles will survive as charged ions, usually with a charge state of 2+, and then you can transport them by some additional structures into the Penning trap. Now, in the Penning trap, we can prepare them such that they make a pure cyclotron motion in the magnetic field, and this is typically about 1 million revolutions per second. And if we now take a spatial position sensitive detector, we can even make an image of the ion motions. I mean, this is a superposition of individual shots. I mean, this is one of the slower motions, but these are individual ions at a certain radius. I mean, the scale here is magnified. So inside the trap, the radius is usually much below 1 millimeter. So usually the volume in which the ions exist is smaller than a cubic millimeter, which is important for reaching the high precision, of course. But I mean, from such an image, in principle, if you measure these different points for a known number of evolutions, you can actually make the frequency measurement. I mean, this is sort of representing the phase of the ion motion. And this phase technique we have developed some 10 years ago. And compared to the conventional technique, it has increased the resolving power by about a factor of 40. And I will show you why this is beneficial. Well, let me show you a few things that we have done in the past. I mean, we have published some measurements in 2022 in this paper, and here you see in red the nuclei that we have measured directly. So in this case, we went up to Rutherfordium 254, and the ones that are connected here in orange, they have a connection by some decay to the ones that we have measured. And if you then perform a mass evaluation, as the atomic mass evaluation people do, also the masses of these orangely covered nuclei are improved by our measurements. I mean, the direct measurements, I can say this is typically measured with about 1 to 5 keV precision absolute, yeah. But since we have heavy nuclei, this of course needs a high statistical precision. And then, yeah, you can improve even masses indirectly of nuclei that are not yet accessible to this technique. I mean, then you can, of course, take the mass measurements and take some binding energies out of it. And this is one parameter, the so-called empirical shell gap. And the data points are here shown in red. And there's some theoretical calculations. I mean, these are microscopic, macroscopic models, for example. And you can see there is sort of a signature of something which is indicative of a shell closure, sort of, yeah, but these are now deformed. So this is a deformed shell gap. That is the main point I want to make here. And you see this is 1.2 MeV. So this is a relatively weak effect in comparison to something, you know, I mean, in lead, the same thing is probably 5 MeV, yeah, just to give you a comparison. Yeah, so here you see a little bit of a more global overview. I mean, meanwhile, we have also measured some dubnium nuclei, and we have in Mainz a program ongoing, the so-called trigger trap activity, where we measure long-lived actinides. And you see we can then cover everything from uranium up to, yeah, maybe at some point, Seaborgium also in our technique. And in the meantime, also our colleagues at RIKEN have started a program, but they use an Ematov, which usually has maybe a factor of 10 lower resolving power and is often not capable of resolving nuclear isomers, which are very prominent. So you have to be careful what you are doing in this region. I mean, here you see an example. These are known isomeric states that have a relatively long half-life. I mean, relative so long that they would be visible in our experiments. And you see many of them have also very low energy. So you need really a high resolution technique because otherwise you might miss these isomers. And here I show you, this is one of what we call an easier example, because here we have excitation energy of the isomer on the order of maybe 150 keV. We have already resolved isomeric states with about 35 keV excitation energy. But this is a nice case. I mean, this was Californium 241. And in the previous experiments a few years ago, we had performed decay spectroscopy. And in the decay work, we had already speculated that such an isomeric state should exist. But in the decay work, it could not be observed. And we now could, with a mass measurement, find that this isomeric state is here and that it has a similar energy to what was conjectured back at that time. Yeah, now let me go to the laser spectroscopy work, because this is quite recent and also quite interesting stuff that I can show you. I mean, one of the things we like to study, I mean, of course, are nuclear properties. I mean, as I mentioned in the beginning, we also want to study atomic properties, but today I want to talk only about the nuclear aspect. And so there are a few things we can do. If we would have an isotope where we have an atomic transition, we would observe a spectral line like this. And as it was also shown in some of the previous contributions, if we keep changing the neutron number, we would see the so-called isotope shift, from which we can infer the mean square charge radius. However, keep in mind, from the isotopes I'm talking about, there are no stable reference isotopes. Yeah? So we have no reference isotope to rely on. So we need atomic theory to calculate for us the field shift, which contains the nuclear volume effect. If we have a non-zero spin and we see a hyperfine splitting, we can also determine from the B factor the quadrupole moment, and from the A factor the nuclear dipole moment. So we learn something about deformation and electromagnetic properties. Now, since we have this rare events, we have to use a sensitive technique. I mean, Alfredo talked about the resonant ionization of plutonium with his outstanding efficiency. We don't have quite 50% yet, but in nobelium we already achieve 15%, which is also not too bad. We have to use only 2 excitation schemes because there are no states known. Yeah? So we can simply not tune it to states that are not known. So usually we start by a 2-step scheme where the first one is the spectroscopy step that is scanned. And for the second one, we often use the so-called brute force, because the cross-section for non-resonant ionization goes down by 5 orders of magnitude, and you can compensate this by using a high-power laser to a good extent. So the method is very sensitive, very selective, and very efficient. We have to deal with low yields, sometimes short half-lives, and as I already said, usually no stable or even long-lived reference ions on which we can practice. We have developed a specific method where we slow down the particles of interest in a gas, 100 millibar argon. Initially, naively, we have thought, well, if you put these particles in 100 millibar of argon, they will simply neutralize. But if the argon is clean, they will, of course, not neutralize, but they will remain singly charged. I mean, about 85% will remain singly charged. So you have to have a different way of neutralizing them. So what we do, we accumulate them with an electric field on the filament, tantalum or hafnium, for example. They will neutralize. Then we can heat the filament for a short time. The atom cloud is evaporated. We hit them with 2 laser beams, and if the laser beams have the right frequency, we create an ion. The ion is then transported by electric fields to a detector, and then we register the radioactive decay to suppress background. Yeah, these are the individual steps. I don't want to go into too much detail. Just basic story is the method is very efficient, very sensitive, and it works. I'll show you a few examples now for fermium element 100 and nobelium element 102. Let's start by element 102, even though it's the heavier one, but this is the one we started with. So this is the first measurement which we did around 2016. Yeah? I mean, this is sort of what we consider a high cross-section meaning something like 2000 nanobarn. And here we go down to about 20 nanobarn. And so here you nicely see the isotopic shift. So if you allow me a little bit more time, I will briefly show you the fermium case. There we have also, added a conventional RIMS measurement with a hot cavity where we can study long-lived isotopes. And just for comparison, this is the measurement we have done in Risiko. This is the fermium isotope 255, 20-hour half-lives. And you see with about 4 orders of magnitude less atoms, we can reproduce the data from 2005 by Hartmut Backe and collaborators. And yeah, then we combined the Mainz measurements. So these are 2 long-lived samples that we got from Oak Ridge. Yeah? I mean, one of them actually was re-irradiated in the nuclear reactor in Grenoble. So it was in 2 reactors. And then after radiochemical separation in our measurement. And these are online measurements that we did at the GSI. I mean, this case, let me see. Yeah, this case is sort of interesting because the half-life is 3.5 hours. So one data point here is 24 hours, just to give you a reference. Now, what is this all good for? Well, we can compare the mean square charge radii that we get with theoretical calculations from various different models. And the main message is all the models agree with each other and with our data. And what we have actually seen, despite the fact that shell effects make the existence of these elements we do not see shell effects in the charge radius anymore. Yeah? So more or less the charge radius is determined by bulk properties. And there is, for example, no steep kink here when you cross the 152 neutron number. This data is under review, is almost accepted for publication in Nature, and hopefully will appear later this year. So with this, I'm finally at my summary. I hope I could convince you that super heavy elements are interesting to study. I mean, out of the 118 elements we presently know, many of them are still not studied in great detail. There is indeed an island of enhanced stability, which is already probed based on alpha decay half-lives. We can meanwhile also use mass measurements and laser spectroscopy to get more detailed information on nuclear properties. And of course, we are continuously extending these measurements and the method developments to go to even lower production rates and even heavier nuclei. And with this, I would like to thank you for your very kind attention.
Thank you, Michael, for this enlightening seminar. Well, now the session is open for questions. Ludia?
Can you comment on the 117, Sigma 117 data on Lubna, which seem to have a larger half-life than the 118?
Yeah, I mean, this depends largely, of course, on the region in the nuclear chart and the neutron number. Yeah, I mean, the thing is, I mean, many of what we have produced is rather neutron deficient. Yeah, so in principle, you can gain in half-life when you become more neutron rich. Yeah, of course, the other issue is that sometimes, I mean, it's important that the data is also measured at least in more than one laboratory, because for small numbers of events, yeah, you can also have uncertainties and misassignments. But I think here it is really simply physics. Yeah, I mean.
In this figure, you show that the land stability should be right.
Yes.
From, like, for instance, from livermorium or fluorine or manganesian. So it seems to me that you need more neutron-rich projectiles. Of course, to produce this neutron-rich, you have to have bigger machines because the intensity drop by many orders of magnitudes. But maybe the production cross-section is three factors. One is the absorption, the second is the formation of the compound nucleus, and the final is the survival. Yep. But as this is more stable, maybe the third term is compensate somehow the initial drop of the intensity of the beam.
Unfortunately not. I mean, there have been a few studies made because initially there was hope, yeah, but I mean, the cross sections don't go up significantly. So the big problem, indeed, you're completely right. I mean, as I said, we need at least 6-8 more neutrons to come to the 184. I mean, one simple thing we can still do, I mean, for californium, you can go from 249 to 251 with some effort. Then you gain 2 neutrons and use the same. But then you are more or less limited because there are no more neutron-rich target materials away. And like you said, the neutron-rich beams, even calcium-50, is already so much down in intensity that it, for the foreseeable future, not a possibility. I mean, people start looking again in other production mechanisms. Of course, the so-called multi-nucleon transfer is discussed, but so far the data, the best data still are from the early 80s from GSI. They seem to indicate you can get more neutron-rich isotopes, but only maybe up to element 106, yeah, because the cross-sections are also small. But we have to investigate other non-fusion approaches to see.
How will the theory describe, or does it describe metastable or isomeric states? And second, would it make some sense to search on very neutron-rich environments from the past that perhaps they could have lived on isomeric states?
Yeah. I mean, that's certainly interesting. I mean, I would say, I mean, of course, there are many theorists that could comment on the accuracy much better than I do. I mean, I would say, I don't think there is a significant, let's say, difference in predicting an isomer in that context. I mean, we know, for example, Darmstadtium 270, yeah, there is a situation where the isomeric state is already longer lived than the ground state. We know experimentally, and we know there might be a few other cases like this. So in principle, it would certainly start to make sense to look, because I mean, a lot of the experiments we have done relied on the decay measurement, and for long-lived states, the decay measurement for small amounts of atoms is not feasible. But for example, the accelerator mass spectrometry people, they have made a large survey. I mean, assuming if there would be certain magic numbers, you would have long lifetimes. They have tried to really scan for samples that are, I mean, along with their homologues, yeah. And they have never found an evidence, and you know, they have this, what is it, 10 to minus 15 gram per gram sensitivity. So on that level, there is not yet anything, and the Mars surface is rather flat. So if there was something, there would be a high probability that they could have seen it, yeah. So in that sense, probably not yet a case, but I mean, I would not fully give up on this. And I mean, there are sometimes claims from astrophysical objects, yeah, somewhere where people say, I have potentially seen a transition that would fit to a super heavy element. So that's why we try to fix the spectroscopy to make such predictions possible. Yeah.
If I may, short question. The titanium 50, I understand that as a beam that there were some initial difficulties getting the high intensities. Is that kind of solved, or?
I mean, that is very much solved. I mean, the different laboratories have different approaches. I mean, we run the titanium 50 beam from a penning source, and we can easily get 2-particle microamps on target. Yeah. I mean, the difficulty is, of course, the high evaporation temperature and the high reactivity. Yeah.
Okay, any other comment or question? So, excuse me.
Somebody earlier had a crackpot question. I have my own. So you mentioned that there were at some point in time, there was a prediction that heavy elements could be inside our Earth. And so they would have been produced presumably by some astronomical sources. Then it begs the question, is there a possibility to do some spectroscopy of elements, heavy elements near neutron stars?
I mean, in principle, if you are able to observe the light, I mean, for example, if you think about the kilonova associated with this, yeah, of course, you can try to look, and I mean, people have identified the easy things like strontium, yeah. So potentially this would be something to look, but you at least need to know from an isotope shift, yeah, what would be the transition to find. And to have this, you need a little bit more data on some of the isotopes that we are studying, but potentially, of course, that could be an option. Yeah? Of course, yeah. Yeah. I mean, there's a lot of uncertainty, so it's difficult to make such a prediction. Yeah. So, I mean.
Okay. Any other question? Okay, so let's thank Professor Blattobel.